Hello everyone, my name is Pierre Harbin, and today I will be showing you guys my final presentation for Physics 220. So it's called Testing Linear Momentum. So without further ado, let's discuss the conservation of linear momentum. So the linear momentum of a particle is defined as the product of the mass of the particle times the velocity of that particle. The momentum of an object in a system might increase or decrease according to the situation, but the momentum of the system will always be conserved as long as there is no external net force acting on it. So here's my table of contents. First, I'll start off with the abstract, which will be the overview of my project, an introduction, which will show you guys my linear momentum experiment, the physical principles, and then I'll end off the video with a demonstration and the results of my experiment. So let's start off with the abstract. To the left was my original project, my original experiment. However, some of the materials were either lost or damaged, and some of the materials had to be changed. But the overall integrity of the assignment and experiment stays intact, with the exact same concepts being checked. So my linear momentum experiment. In my experiment, I'll be demonstrating linear momentum, and I'll also demonstrate whether or not it's possible to demonstrate linear conservation in the real world context. To the left, you see a ping pong ball that I will release from an incline, and then there's another ping pong ball of equal mass at the end of the track. So once those two balls collide, if linear conservation is true, or linear momentum conservation is true, then the first ball should stop, and the second ball should move with the same speed as the first ball. And so the materials that you'll need is simply ping pong balls or balls of equal mass. You'll need a track, and a ramp or incline is optional. You don't necessarily need one, and it's probably best to do it with no incline. However, if you do add an incline, it does add some more cool concepts that you can check. And even in my demonstration, I have an incline that I'll show. You'll have a ruler to track the displacement of the second object, and a stopwatch in order to be able to track both the speed and the time of the experiment. So in the linear momentum experiment, I want to base my experiment on chapter 9, linear momentum and collisions. So to be specific, I'll see if energy will be transferred between object 1 to object 2. Now, originally I would have accelerated a ball towards another ball of equal mass and measured the energy transfer by calculating the displacement of the second ball afterwards. And this test demonstrates both conservation of energy and the conservation of linear momentum through a simple experiment. However, thanks to the science lab, although I lost some of those materials, I was still given the opportunity to use the science lab room and use the carts and tracks for this experiment. So the only materials that were changed is just from balls, I went to the carts, and from having a paper tube as my track, I had a metal track for this one. So the physical principles that you need for this starts off with the linear momentum equation. Momentum is equal to mass times velocity. And in order for conservation of linear momentum to be true, the initial net momentum has to be equal to the final net momentum. We'll have the velocity equation, which says that this velocity is equal to distance over time. And this is how we will track the speed of the objects. And then you have the conservation of energy, which is the initial energy, the initial net energy should be equal to the final net energy. And so let's go into my demonstration. And so what you can automatically see right now is that as I release the cart 1, which is on the right side, it approaches and collides with cart 2, which is initially at rest and ends at rest. And so throughout this whole demonstration, cart 1 starts with a velocity of v, and cart 2 has a velocity of 0. And so at the end of the demonstration, cart 2 has a velocity of negative v, and cart 2 is still at 0. And so what we can see here is that the magnitude of the demonstration, the magnitude of cart 1 is not changed. All right, the speed is not changed, and even as you can see, as I let go of cart 1, it actually returns back to the original location that I let it go from. And this is the reason why I actually had it on an incline to kind of show that, I necessarily don't even have to really push it, right? I can let gravity do its thing, and you can actually see that it will just return to its original position. And so if this experiment just continued on for maybe another 5 seconds, maybe a minute, you'll notice how the dampening will occur. And so this dampening occurs due to the effects of friction. Now, in a perfect idealistic scenario, you would have a vacuum and a perfectly frictionless surface, right? And so these collisions, these elastic collisions would occur for forever, for infinity. But due to the effects of friction, cart 1 is slowed down, and you actually can physically hear that friction is happening from the tracks as they rub on, as the carts as they rub on the track. And so here's my result. Not sure why that's happening. Okay, and so here's my result. So these are the results for cart 1. You can see as I release it from the position, and it collides with cart 2, the velocity stops, and the position of the object stops. And it goes back, and it returns, and you can see that it is almost perfectly identical as the object approaches, as cart 1 approaches cart 2, and you can see as they collide, a perfect, almost symmetrical output comes out. And this shows us that linear momentum and the energy of the system is conserved. And so much special thanks to the science lab for giving me the opportunity to use the room and use the carts and tracks for this demonstration as I end off this semester. And a special thanks to everyone that's listening through my presentation. And I hope you guys have a great summer. Thank you very much.